In a world that appears overwhelmingly chaotic, could there be a hidden order? Welcome to The Science of Chaos, Chaos Theory Explained. Today we're venturing into the captivating domain of chaos theory. This intriguing field of study seeks to detect patterns and predictability in what might initially appear as completely random. It's a fascinating world where the seemingly chaotic finds a semblance of order. You might be thinking, chaos? Isn't that about pandemonium and disorder? Well, not exactly. When we talk about chaos in the context of chaos theory, we're referring to something quite different. We're not talking about anarchy, but rather we're exploring complex patterns of behavior in systems that are highly sensitive to their initial conditions. This sensitivity to initial conditions is a phenomenon famously known as the butterfly effect. Now you might be wondering, what's this butterfly effect? Picture a butterfly flapping its wings in the heart of the Amazon rainforest. This simple act, according to chaos theory, could set off a chain of events that could potentially lead to a tornado in Texas. While this is a metaphorical example, it illustrates how tiny variations can lead to unpredictable outcomes in complex systems. This sensitivity is what makes predicting certain things, like the weather, stock markets, or even your morning commute, profoundly challenging. So we're about to delve into a world where order and chaos coexist, where randomness finds a pattern, and where predictability and unpredictability intertwine. We're about to embark on a journey that will take us deep into the heart of chaos, and hopefully help us find the hidden order within. So, are you ready? Buckle up as we embark on a journey to unravel the mysteries of chaos. Chaos theory, at its core, is about finding the underlying order in apparent randomness. It's not about disorder, but about complex patterns of behavior in systems that are sensitive to their initial conditions. This sensitivity is known as the butterfly effect. But what exactly does this mean? Let's picture ourselves in a bustling city, amid the seemingly random rush of morning traffic. Now consider that each driver's route and speed is influenced by countless factors: the time they left home, the weather, the flow of other vehicles, and even the mood they're in. Just one driver hitting the brakes can create a ripple effect that alters the routes and timings of hundreds of others. This is an example of a complex system where small changes can lead to unpredictable outcomes. Now let's imagine a weather system where a multitude of factors, from temperature to air pressure, interact to form weather patterns. Meteorologists use highly sophisticated models to predict these patterns, but these predictions often go awry. Why? Because even the tiniest variation in the initial conditions of these models can lead to vastly different outcomes. This is the butterfly effect in action. The idea that a butterfly flapping its wings in Brazil could potentially set off a tornado in Texas. The same principle applies to the stock market, where millions of individual buying and selling decisions, influenced by a myriad of factors, interact to form complex patterns of prices and volumes. Small changes in initial conditions, such as a minor news event or a subtle shift in investor sentiment, can trigger large-scale fluctuations. So the butterfly effect is not just about butterflies and tornadoes. It's a fundamental concept in chaos theory that helps us understand why it's so hard to predict outcomes in complex systems, whether it's the weather, the stock market, or your morning traffic. This sensitivity to initial conditions, this dependence on the tiniest of changes, is what makes predicting the weather, stock markets, or even your morning traffic profoundly challenging. The journey of chaos theory began in the 1960s with meteorologist Edward Lorenz. This is a tale that starts with a weather prediction model. Lorenz, while running a series of weather simulations, made a minor alteration in the input data. The result? A drastically different weather pattern. This was the birth of chaos theory, and the realization that even minute changes in a system's initial conditions could lead to wildly differing outcomes. This seemingly insignificant discovery shook the scientific community to its core, challenging the deterministic view of the universe. The discovery suggested that not all systems are predictable, even if their underlying rules are known. It was a profound leap in our understanding of the complex systems around us. Throughout the 70s and 80s, chaos theory continued to evolve. Scientists from different disciplines started recognizing chaos in their fields. Biologists saw it in population dynamics, economists in market fluctuations, and physicians in the rhythm of the human heart. Chaos was no longer a mere mathematical curiosity, it was a ubiquitous part of nature and the universe. The development of chaos theory was a journey of discovery and understanding. It taught us that unpredictability and complexity could stem from simple rules, and it opened our eyes to the hidden patterns in the seemingly random world around us. From then on, scientists across disciplines began to see chaos everywhere, from the rhythm of the human heart to the growth of populations. To truly grasp chaos, we must understand a few key concepts. Let's start with strange attractors. In the realm of chaos theory, an attractor is a set of numerical values toward which a system tends to evolve, regardless of the starting conditions of the system. Now, when we speak of a strange attractor, we're referring to an attractor that has a fractal structure. This means it's an attractor that can be split into parts, each of which is a reduced-scale copy of the whole, a property called self-similarity. Moving on, let's delve into fractals. These are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. Driven by recursion, fractals are images of dynamic systems, the pictures of chaos. They're everywhere in nature, from the leaf design of a fern to the pattern of a snowflake. Finally, we have Lyapunov exponents. These are a measure of the rate of separation of infinitesimally close trajectories. Simply put, they tell us how sensitive our system is to initial conditions. Positive Lyapunov exponents are indicative of chaos, as they show that our system diverges with time, leading to the unpredictability we associate with chaos. Together, these concepts help us understand and visualize chaotic systems. Chaos isn't just a theory. It's all around us. In fact, it's an integral part of how our world functions, both in the natural world and the man-made realm of technology. Let's take a journey through the expansive field of meteorology. Weather patterns, as we've already touched on, are a prime example of chaos theory in action. Small changes in atmospheric conditions can lead to drastically different weather outcomes, making long-term forecasting a challenge. But thanks to chaos theory, meteorologists have developed models that, while not perfect, allow us to predict weather patterns with a degree of accuracy that would have been unimaginable a century ago. In medicine, chaos theory is helping us to understand complex physiological systems like the human heart. The seemingly random fluctuations in heart rhythms aren't as random as we once thought. These patterns, as chaotic as they may appear, can provide crucial insights into heart health and disease. In the realm of engineering, chaos theory has proven to be an invaluable tool. From optimizing traffic flow in sprawling urban cities to improving the efficiency of jet engines, the principles of chaos theory are helping engineers to design better, more efficient systems. And what about economics? The unpredictable ebb and flow of the stock market, once thought to be completely random, can actually be studied and understood through the lens of chaos theory. By recognizing the complex patterns within the chaos, economists and traders can make more informed predictions and decisions. Chaos theory even has a role to play in epidemiology. By understanding the chaotic nature of disease spread, we can create models that predict the trajectory of epidemics, helping us to prepare and respond more effectively. So you see, chaos theory isn't about disorder. It's about finding order and patterns within the chaos, whether that's in the rhythm of a heartbeat, the swirl of a weather system, or the fluctuation of the stock market. It helps us understand patterns in the stock market, design more efficient engines, and even predict epidemics. So, as we see, chaos isn't just about disorder. It's a realm of science that finds hidden patterns in what seems like randomness. It's a fascinating field that deals with complex systems sensitive to their initial conditions, a concept embodied by the metaphor of the butterfly effect. From its inception in the 1960s with Edward Lorenz's weather simulations, chaos theory has evolved to encompass key concepts like strange attractors, fractals, and Lyapunov exponents. These terms might sound exotic, but they help us visualize and understand the intricate dance of chaos and order. Chaos theory extends its reach from natural phenomena to technological applications. It lends insight into the unpredictable weather patterns, the rhythm of our hearts, the design of efficient engines, and even the prediction of epidemics. Chaos theory, then, is a tool that helps us make sense of the seemingly nonsensical to find order in the disorder. Thank you for joining us on this journey into the mesmerizing realm of chaos. Hey there. We hope you found this journey into the realm of chaos theory as fascinating as we did. If you've enjoyed the video and learned something new, why not give it a thumbs up? Your likes help us understand what content you find valuable and want more of. And if you haven't done so already, hit that subscribe button. By subscribing, you'll be the first to know when we release new videos exploring other intriguing theories and concepts. Got a friend, a classmate, or a colleague who might be interested in chaos theory? Don't forget to share this video with them. Who knows? You might spark a new interest or a fruitful discussion. Remember, every like, subscribe and share helps us bring more insightful and captivating content your way. We appreciate your support and we look forward to keeping you informed and entertained. Thank you for being part of our community.